Let's discuss two thin lenses with a focal length of magnitude 12 centimeter. The first is a diverging and the second is a converging lens and are located 9 centimeters apart. Let's go ahead and draw this so we can have a better picture. So we have a diverging lens. So call it lens 1, and we have a converging lens. So call it lens 2. The distance between these two lenses is given to be 9 centimeters. So let's name it distance equals 9.00 centimeters. And then we know that the focal length of both of them is 12 centimeters, but for the diverging lens, the focal length should be negative because it's a diverging lens, 12.0 centimeters, and f2 equals positive 12.0 centimeters. Now, an object 2.50 millimeter tall is placed 20 centimeters to the left of the first diverging lens. Let's put the object on our principal axis to the left of the lens. Of course, my picture is not to the scale, but I am going to approximate the object to be here. Of course, this is not 2.5 millimeters, but I'm going to call this an object, and we want to pull this information into our list. So height of the object, because it is the how tall object is 2.50 millimeters tall, that means height of the object equals 2.50 millimeters, or that could be written as 0.25. Let me put it underneath. Or it could be equal 0.250 centimeters. Then let's read the question. First question: how far from this first lens is the final image formed? So we want to find out the distance of the final image, question mark. For the A, is the final image real or virtual? So what is the height of the final image? So for the A, for the part B, we have real or virtual. For part C, we want to find out height of the object, and we want to answer the question erect or inverted. Okay. Now, to find the distance of the image, we need to understand one thing, that the object is the light from the object is going to pass through lens 1, create the first image, and that first image is going to serve as an object for the second lens, and then the light from the image from the first lens, which is the object for the second lens, will pass through the second lens, create the second image, which will be the final image, and then we will try to find the distance. So that's why we're gonna focus on lens 1 first. Let's just write that down. So lens 1. I'm gonna use different colors so we can identify it. So let's pull it out. So for lens 1, the focal length is negative 12 centimeters. And then distance of the object, I'm gonna call it 1, is 20 centimeters. To find the distance of the image, for the first lens, I can use 1 over f equals 1 over do plus 1 over di. If we simplify and solve for di, this can be written as FDO and the object minus F. Now for my case, I'm going to plug in the numbers. So I have a negative 12.0 centimeters times the DO1, that be 20.0 centimeters divided by 20.0 centimeters minus negative 12.0 centimeters. So that will give me a value of negative 7.5 centimeters. So which means this is negative 7.5 centimeters, means it's to the left of the to the 7.5 centimeters to the left of the lens 1. So let me write that, left of lens 1. Okay, so and let's try to find the magnification, how it has changed. So I'm going to call it magnification due to the lens 1 equals negative the image from first image divided the object 1, and that equals negative 7.50 centimeters divided by 20.0 centimeters, which equals positive 0.375, which tells me that the image is upright and it is reduced. So if I go back to my picture, it seems like the distance is negative 7.5. That means somewhere here with a reduced size, this is the image 1, which becomes an object for my lens 2. I'm going to call it object 2. So while this one was our original object, here is the object 1. Now now we're going to focus on object 2 and have the light pass through our lens 2. Okay, so let's go ahead and then do our calculations. Lens 2, what we have now, we have f2 equals positive 12.0 centimeters, and distance of the object 2 this time equals, if we take a look here, so from the object 2 to the first lens, we have found it equals 7.5 centimeters, and then our object 2 distance DO2 would be 7.5 centimeters plus 9.00 centimeters, which in its turn is equal 16.5 centimeters. So I'm going to put that information here in my list, 16.5 centimeters. And then I can use, and then again, I'm going to find the distance of the image for the second one, which is the final image. So I'm going to use the same equation as we found earlier for distance of the image. So distance of the image 2 equals f2 DO2 divided by DO2 minus f2. So let's plug in the numbers here. We'll have 16 to positive 12.0 centimeters times DO2 is 16.5 centimeters divided by 16.5 centimeters minus 12.0 centimeters, which will give us 44.0 centimeters. and that would be 40, that is positive, which means that is to the right of lens 2. So this is to the right of lens 2, which means our new image is somewhere to the right of lens 2. So it should be somewhere, what was the value for us? 44, right? So it should be quite far away. So if we put a little bit longer distance here, then our image will be somewhere here. And by the way, we need to find out whether this is inverted or erect. For that, we need to figure out the magnification. So let's do that before we go ahead and try to identify the spot. So M2 equals negative DI2 divided by DO2. That equals a negative 44 centimeters divided by 16.5 centimeters, which equals negative 2.67. But that is not actual magnification for our image, because remember, the magnification, the total magnification will equal M total equals M1 times M2. So what did I have for M1 is positive 0.375 and M2 is negative 2.67. Let's multiply them together. Positive 0.375 times negative 2.67, and that equals negative 1.00. So what does this mean? It means that our image is actually inverted because of this negative sign, inverted. But the magnification is, if we find the height of the image, that would be M total times H of object, which equals negative 1.00 times 2.5 millimeters, which is negative 2.5 millimeters. So when the total magnification is 1, that means the size didn't change of the object. So I can this negative tells me it's inverted, and 2.5 millimeter means it didn't change the size. So if I go back to my picture, then I would have to draw the same original object size somewhere here, inverted. Okay, so this is the final image, and the distance from here to here is 44 centimeters. But let's recall what our problem is asking. What is the height of the final image we found? How far from, okay, the part A, how far from this first lens is the final image, which means we need the final image from here all the way to the final image, which means 44 plus 9 centimeters. My final result will be distance from lens 1, distance of eye, okay, image, okay, DI from lens 1 equals 9 centimeters plus 44 centimeters, which equals 53 centimeters. So finally, let's just box all our answers So this part is for part A, and as an answer, height of the image, final image, right, is the part C, and final image real or virtual. We didn't say whether this is real or virtual. So if you get a DI, where is it? DI that is positive, right here, positive means it is a real image and not virtual. So that's my part B. And finally, the final height would be 2.5 millimeter, and this means it's inverted. So this is part C. Okay, thanks for watching and stay tuned for more.